Good to see everyone. Good to see people in the back as well. All right, you have two rows to the setup, so I can walk here, and I guess I can show something once I have something to show. I guess. All right. So today we will look at the basic way of solving problems with search. So this will be sort of familiar ground to most of you, right? Since we know search algorithms, right? So how to plan something, right? So basic, simplest agents. We'll be talking about agents which now have full information, right? Problem-solving agents, planning agents, and again, this will cover some basic, well-known algorithms, right? So we know the idea of this intelligent agent, and today we'll look at informed decisions, right? And also the ones we don't have information, right? So in some ways this is a slightly different way of looking at algorithms for shortest paths, things like that, but a little different a way of looking at from the perspective of an intelligent agent, right? And of course also there's discussion of complexity, right? So this will be the simple agent would be a search agent would be somebody, something like Google Maps, basically, right? You're trying to go from somewhere to somewhere, right? You're building a Waymo bot, a Waymo driving car, right? And you want to get from one city to another city, basically, right? So obviously, again, what suggests underneath there's going to be some shortest path algorithm, right? But how do we put this shortest path algorithm underneath or intelligent agent, basically? How do we apply it, basically? Right. So scenario, the case study will be Romania. That's because it's in the book. We could, of course, apply Latvia or any other country. Right. It mentions Bucharest and Arad. Who has been here to Romania? I don't know. One of you, right? So, how was
quite interesting.
Yeah.
It was this summer. I visited Bucharest.
Uh-huh.
Brasov.
Okay. Brasov. It's in the middle, right? Bacău? No.
No, it's close to mountains.
Okay. How about Arad? You didn't get that far, right? No. Okay. Right. So you have multiple choice. You have this agent, right? The agent is on vacation. They're in Arad, right? And they need to reach Bucharest, right? So lots of choices where to go, right? So again, the challenge, of course, we could, in an unknown environment, we could just do things in random, right? Go somewhere, right? Are we going to end up where we want to be? Probably not, right? If we just choose randomly, right? We need some strategy, right? So sometimes, again, choosing randomly might be actually an option, but that's not for today. That's for next chapter, basically, right? So we need an objective. Again, formally, goal is Bucharest, right? So anything that leads to Bucharest, right? That's our rationality. That's our rational, intelligent agent, right? We're not going to Riga. We're not going to Paris, right? So we develop this abstract model of our world, right? So this will mean, of course, some sort of graph representation, of course, right? But it could be something else. We have other ways of representing, right? But again, the challenge is if you don't have any pre-existing knowledge, how do you build this, right? So we're gonna simulate our actions, and again, the question is what kind of level of abstraction where we live, right? At this moment, right, our agent is gonna be sort of like abstraction will be that it knows how to go from one city to another city, right? In real life, going from a city to city on a single road, right? Going from Riga to Tukums is not a trivial task, right? It involves many other subtasks, right? But at this stage of an agent, right, it seems, okay, we have a solved problem how to go between cities, right? We just need to basically execute this plan, basically, right? So that makes our life simpler. So this is, again, we start with a simple example, right? Because if you build up on this, you end up with a undeterministic, unknown environment. You have snow, you have things happening, right? For here we assume that once you punch in, Tukums, so the next city, right? You have a simple way of getting there, right? So again, so this is we have fixed actions. We have a certain environment, right? We have fully observable, meaning we know everything about our world here, right? So it's a fixed. So do this, do that, basically, right? So again, makes things much simpler because we can apply a lot of known algorithms and it makes life easy, right? So not gonna be always that easy, right? But it's a good step, good starting step, right? So it's an open loop system, right? So this means perception. Remember percept. Remember our first lecture, our agents, right? We have perceptors, how we sense the world, right? On actions. Here, unless there's a road closure, right, in the middle of you're driving, right? At this stage, we don't ignore that. We assume we know we're gonna get there, right? So, again, it's possible, right? It's gonna be partial observed. Maybe we don't know something about the road conditions. Again, maybe there is like I said, road closure is a classical thing you want to improve eventually, right? But how to solve this simple problem, right? You all know how to do it. What do we use? What's going to be our hammer? What's going to be our tool? Some sort of shortest path algorithm, right? Probably, right? Probably just good old Dijkstra, right? Probably something like that is going to be driving our model. When we have everything known, right? We can have we can sort of supply all this information, punch in a well-known algorithm, right? And we have a set of instructions for the bot or for the agent to do, right? Simple, right? So we have formally, like this book is very, formally we say, okay, state possible states, meaning where you are, right? In this case, we define our state space as a city where your car or your bot or your agent can be, right? Initial starting point, which would be, of course, Arad, right? And the goal, right? Here in this example, the goal is only one, Bucharest, right? But you could, of course, imagine you have maybe, you don't particularly care about Bucharest, you just want to go anywhere that's not Arad, right? So that could be easy, that would be even easier, right? If any city that's not Arad works for you, you just punch in, then random approach would work, you go to your robot taxi and you say, okay, take me anywhere, right? And, robot taxi says, what's anywhere, right? And it says, you have to supply some city. Again, that Johnny Cab from Total Recall from 1990 movie comes to mind, right? Schwarzenegger had the problem. He said, I think go anywhere, right? And Johnny Cab didn't understand that instruction, I think, if I remember correctly. It's been a while since I saw that movie, right? But so that's of course issue, right? Where you want to go. And of course you need some sort of is goal. Are we there yet? Mom, are we there yet? Are we there yet? Are we there yet? Yeah, is goal method, right? We need that. And of course, we need some sort of action, way of doing it, right? So here, of course, a transition model, you supply action, right? And you get something, you end up somewhere, right? So, it's possible, most likely you will need also some cost, right? Costs can be positive, right? It costs something to go there, right? And cost can be negative, right? What would be a negative cost example, right? Well, somebody's paying you to go somewhere, right? We can't travel back in time, but as far as costs of money, right? You have a negative cost, meaning somebody gives you money to go somewhere. It's possible, right? So, but for now, of course, we'll deal mostly with positive costs, meaning it costs you to do something, right? And we need those for estimating or actually, evaluating how well we are doing, right? How much money, how much time, how much gas, or whatever resource, electricity, our agent spends on the actually achieving the goal, right? So that's a formal definition again. And this thing is this approach, right? I mean, it seems like, okay, see, just apply shortest path algorithm, and you're done. But formally, you can apply this approach to other problems. You name a problem, right? As long as there's a goal, right? You can set these definitions. Start, end, and so cost, and so on. So solution will be, well, a set of actions, sequence, right? A path, and of course we're going to have an optimal solution, which will be the one with the lowest cost, right? And in this first example, we're going to use only positive action costs, right? Why? Because if you remember for algorithm class, what happens if you have negative costs, then you need to use different algorithm, right? You can't use Dijkstra, there's only certain algorithms you can use, right? So graphically, of course, you can use map of Romania, right? So we made an abstraction from our map into this formal model, right? Again, extremely simplified, right? So we remove the things, right? Because if we try to make things, completely, to say everything we need to do, put a foot onto the pedal or maybe actuate something, right? We need some level of abstraction, right? Otherwise, we'll not get anywhere, right? If you start thinking too much, right? You need to have things which are already solved, right? If you have to write a agent or bot only in machine language, you will not get very far, right? Okay, why don't we have any image? Oh, okay, I guess I have to do something. Okay, all right. Now, so you need some abstraction, right? So your goal when you're building something, when you're solving a problem, is you want to build an abstraction, but you want to hide things, right? But you want to keep some, you want to maintain the ability, because it could be an abstraction, go to Bucharest, right? And say, okay, I'll just let Google Maps do it for me, right? And in a way it would work, right? But it would be, maybe it would completely remove the problem here at all, right? You say, okay, it's already solved problem. I'm not going to worry about it, right? So again, you need some abstractions, right? So using this approach, right? We can basically apply this to pretty much many problems, right? So standardized problem, of course, is concise, right? Real life problems, of course, will have a lot of extra details which make your life complex, right? So here's some standardized problems. Again, something like this. I will give you probably on Thursday. There will be a homework, right? Something like a two-world vacuum problem, something like that, right? You define a two-dimensional grid, right? Agents can move, right? You have some dirt, right? And you can start somewhere. You have a suck left, right, or up, down action. Yeah, and by the way, I want to talk about this vacuuming problem about the cost function. If your goal is to, how should I say, vacuum as much dirt as possible, right? If your cost is defined by vacuuming dirt, right? What's one possible, and you have a command or action dump dirt, right? What will happen? The bot, right, if you make it, it can dump dirt and then it will keep vacuuming and then dumping dirt, because the cost function will be, you are vacuuming, your success is defined by how much you vacuum, right? But you also dump dirt, but that's not accounted for, right? You have to be very careful how you define your success and your goals, right? So you probably want some sort of function, something a little bit more, how should I say, less ambiguous, right? So, if you let the bot, your agent, dump dirt, right? And then again, suck it up again, right? It will lead to potentially the agent, doing something you don't really want, right? So, yeah, so this is one example, right? So, now, 8 puzzle problem, right? Something like this. You see, how do we call this in Latvian, right? 8 puzzle or 9, 15 puzzle. I think it's, Anyone has played this one? This is kind of like single player game basically, right? Anyone has solved this? Yes. I don't know, on a really boring train ride or a car ride, right? So how would you define success? Well, of course, you define success by all of these being in an ordered fashion, only one success state, right? Beginning states, right? It could be whatever you have, right? But no, this book mentions there's about 200 trillion states, right? Possibly, right? 8 by 8 grid. That's if you have 8 by 8 by grid, right? But a 15 puzzle, right? So again, so your original starting position could be huge, right? So building an agent which solves this, right? You need some sort of movement, right? Again, you have starting position, you have these transitions, and you have the goal, right? And again, but it can be, if you think about it, it can be solved similar approach like your car example, Romania or Latvia, right? Similar idea actually, right? You have a goal, right? And you have some starting position, and you have moves basically, right? So there are variations, right? So 8 puzzle, yeah. So this is interesting problem, something called Nuss number problem. Donald Nuss is, of course, famous computer scientist, one of the last living legends, right? And one of the things he mentioned demonstrated infinite state spaces, right? So here, right, you say, okay, here we have, we have many moves, just like in chess or solitaire, right? You have many moves, but it's finite, right? It's actually possible to have infinite state spaces. So his idea was this, he came up with this game. Reach any desired positive integer, starting from number 4 through a sequence of specific moves. So what kind of moves did he allow? So, you start with 4, right? You only have 3 moves. Square root, floor, and factorial, right? So factorial only works on integers, as you well know, right? So, so how can we do this? Let's look at an example, right? So potentially the number of moves is infinite, right? You can keep going up, right? But I don't know if he proved it. So how do we get to 5, right? It gets pretty far, right? So right, so we can get to very big numbers, right? So we'll look in a moment. We'll look at the solution. How to go from 4 to 5 using only these two operators: square root, floor, and factorial, right? I mean, it's kind of weird, right? So 4. How do we do this? Well, so it means you need, of course, to get 5, you need something that you take square root, right? You get something 5 something, then you can take floor, right? So you need like 26, right? 26 square root would be 5 something, you get floor. But we have 4, and 4 factorial is how much? How much? Yes, and that's not good for us, right? Not good for solving it quickly, right? So, kind of interesting game, right? So let's try this. Let's try playing this game, right? So I'm going to import square root, factorial, and floor, right? So 4, right? Print n, factorial again, right? And then we're going to do a bunch of square roots, right? And then we're going to floor it, right? And I think we'll get there. Let's take a look. Yeah, I think it works. So 24, look at this here, right? So factorial of 24 is this big number, right? Then we take a bunch of square roots and we get to 30, right? And that's 5 something, and we solve it, right? But I have not read his discussion. Do we have a general strategy for getting there, right? We don't really, right? So I don't know if he proved. I think he claimed you can solve this. It will work for any number, right? So how about 6? Could you guys do it for 6? I don't know, right? I mean, we don't really have a good evaluation function, because like you get this huge number, right? Are you making progress? I don't know. Maybe you need to make another factorial, right? And then you get a really huge number, right? if you take a factorial from this, right, it's not going to fit in our computer, right? Factorial of this is just going to break our computer, right? You know, two truly large numbers. So, but basically what this means is, of course, this example shows that it's your solution space is potentially infinite, right? In this particular game, right? So for these type of problems, there's lots of examples. Of course, route finding, you know, Google Maps, right? Airline travel, you know, tour planning, VLSI layout, which is very large scale integration for making computer chips, right? Robot navigation, obviously, and automatic assembly sequencing. So for airline travel, right? You guys all probably traveled during. You've been traveling, right? So you have a location where you are right now. Maybe you have some fare bases, maybe some, you know, where you're going, right? Initial state is, you know, let's say Riga, RIX, right? Actions, you know, take any flight, right? Transition model, right? Goal state, right? But again, things get complex if you add things like, do you want to travel economy only, right? Do you care where you sit, right? Lots of things can make this problem more complex, right? Then you have touring problems, of course, traveling salesman problem, right? You want to have a set of locations, you don't have a single goal in mind, maybe you just want to cover everything, but you want to pay the least, right? There's a very large scale layout problem, right? You have, how do you lay out a modern computer chip, which is billions of semiconductors, right? How do you route the connections, right? Very complex, but very crucial, right? So, what else? Robot navigation, right? Build a bot which moves around, right? Lots of challenges, of course, sensor errors. Again, we don't have full information. We don't have full information, right? So, assembly sequencing, right? Things like that. So, the idea, of course, is we use some sort of search algorithm, right? So, we explore, we have a starting point. Maybe I'll do again, I'll use my paint, right? Maybe I'll use my paint again. Yeah, can I use, oh yeah, I can use paint here, right? Maybe big, oh, here we go. Right, so where's my pen? Is that pen here? Yeah. So we have our starting city, right? Right, let's think, I'll call Arad, right? Right, and then you have this possible search space. You can go to, I don't know, whatever B, right? I don't know. The cities, I should probably do Riga, it would be easier, right? I'll do Riga because it's easier. I don't know the offhand, right? We call Riga, right? And we want to get to, I don't know, call it Riga, right? Right, and then you go to Uogre, right? Right, and then you go to, I don't know, Jurmala, right? And you want to get to Tukums, right? Somewhere, right? That's your goal state. So that's the starting state, right? Starting to do this, oh, this here. Oh, yeah. Where's my, how do I get the full paint? How do I get full screen? Let's see. Well, anyway, so this is start, right? Starting, go, start, state, right? And then we have this sort of like Uogre, right, of course. And then you have, I don't know, Jääkapils and so on, right? I'm just skipping things, and maybe Jelgava, right? Right. And of course, maybe you have Tukums here, right? Right. And this is your goal, right? Right. And again, you're making choices. Again, you have, maybe you have a search, but you don't know. I mean, here our eyes know where we go. We go Riga, Jurmala, Tukums, right? But the intelligent agent does not have this knowledge, right? We have to build it, right? We have to sort of have some sort of approach. How do we check it, right? So we need some sort of, you know, some way of exploring the search space, right? We have a set of decisions to make. Again, if we are there, are we there yet, right? And then we, okay, success, right? So, again, depending on the problem, there's no like one solution for this problem, right? Because it depends how your search graph is oriented, right? So, right. So there's two things. So there's a state space. That's where, you know, Riga, Tukums, Jurmal. That's where you could possibly be, right? That's your state space. But search tree is what you are doing, right? What you actually actions you took, right? So notice that we could possibly, right? Like in this example, right? You can keep going, right? Each node has a unique path back to the root, right? So again, because you remember that trees don't have loops, right? Trees don't have loops. No, right? So we need some sort of strategy. On one of the strategies, you know, best first search, right? We have some function, right? Evaluation, which gives us idea, right? Like the cost, right? So the cheapest, you know, or best, right? Or giving you the biggest price, right? Right. So best first, right? If you keep exploring it, basically, right? So you check. You have this frontier, right? The best first search is basically Dijkstra is one of the examples again, right? You have a function, the score gives you scores, and you have this. You are expanding this frontier, right? You keep going, right? And if you reach the goal, you have a solution, right? So something like this, right? You have a function, you have a state, you have where you came from, you have action, and you have a cost. Essentially, this is basically, again, exploring the graph, right? And you always check that the cheapest one or best, which you have not yet done, basically. Okay, why is my screen again? Okay, right. So you need to store the frontier, right? Where you have not, which is like the things you're not sure yet, right? The things you're not sure yet, basically, right? And again, all of you have taken, I think all of you have taken algorithms class with me, so you know we use some sort of priority queue, right, structure to probably implement Dijkstra in this example, right? So, of course, the problem is, let's say you have 10 by 10 grid, right? Agent, you know, will need maybe 9 moves. It's diagonal. Let's assume it's diagonal moves allowed, right? But potential moves, right, is 8 to the 9, which is like 100 million paths, right? But most of them, of course, will be redundant, right? So this means at some moment you will need to have some memory, where have you been, right? So because you don't want to keep trying, don't want to go where you have not, you know, where it's already, you know, there's no point to repeating yourself, basically, right? So maybe you want to remember, right? Maybe, so you have to decide when you're exploring your problem, do you need to store this previous memory? Do you need some sort of search memory where you've been to, right? So graph search, you probably want to have a redundant, check for redundant paths. Tree-like search, right? You don't have loops, you might not need to check. So, again, so how do you evaluate these search algorithms, right? Whether actually you can always find a solution, right? Whether it'll find you a solution or the solution, right? Also, how much time or time complexity, right? How, if you have a big search space, is it going to be, you know, exponential, polynomial, right? You know, is it n square, is it n cube, right? Also, do you need how much memory you need, right? You're building a simple bot, maybe you don't have much RAM, right? Probably, right? So completeness, right? Also, are you going to be exploring whole state, you know, all of these possible states, right? So if you have infinite, right? Then if you have possibly infinite state space, then by definition you can't explore everything, right? So you need some sort of strategy. Now you can't just check everything, right? You cannot use brute force, basically, right? And remember I told you in algorithms, right, start is brute force. But if you have this infinite state space, you can't use brute force. It's not gonna work. You just keep running, loop forever, right? So you need some sort of way of exploring, right? So infinite grid, right? A spiral path, right? It's systematic, but you might not find a solution, right? So again, time-space complexity, right? You will have some sort of space graph, right? Of course, it will involve the number of vertices, number of edges, right? So probably something cubic, probably, maybe quadratic, maybe, right? So we still have some time, yeah, a couple minutes, right? So if we don't know anything, right? We don't have any information where we're going, right? We don't have any domain-specific knowledge, right? So they are so-called uninformed, right? We don't have basically we don't have cheat codes, right? Which means, of course, in terms of maps, like we don't have some Euclidean, some function, right? We don't have an eval function, right? So these are like basic strategies. So breadth first search, right? Which means we start one level deep, we check everything, and then we keep going deeper, right? Check everything, right? You know all this by now, right? So breadth first would be, right, something like this, right? This is all, I think, good stuff, right? You start here, right? You check 1, 2, 3, right? First level, right? You check again, maybe 2, maybe you have 1, 2, 3, maybe 1, 2, right? So this is, your choices, I don't know, whatever it is, right? But you keep trying all of these variations, right? And maybe eventually, right? This is a goal, okay, you win, right? So breadth first, right? So again, you don't know where you're going, right? But you have the approach, breadth first, right? So what's the problem with this approach? It's completely valid strategy, right? What's the problem?
Inefficient?
Well, it could possibly just explode, right? Right, and you keep going, right? Oh, come on. Oh yeah. Okay. So if you don't have any cheat codes, right? You can keep exploring everywhere, right? Completely wrong direction, right? Completely wrong direction, and it is going to be very inefficient, right? But again, if your search space is small, it's a possible strategy, right? Breadth first search, right? So, and of course, again, we have variations on this theme, right? So, what kind of efficiency could we get, right? Maybe you have a first out cube, some data structures you can use, right? Maybe we have some sort of raised states, right? Maybe, right? Now, Dijkstra algorithm, of course, right? Best first search, right? Best first, right? We have some sort of costs, right? You all remember Dijkstra, right? All written, right? So, uniform cost, right? We have a cost function, right? So we don't just randomly check breadth first. We check the cheapest or the best first, right? So in our path right here, right? We don't just completely randomly check, right? We have some way of checking our possible solutions depending on the cost. We are storing these possibilities in some sort of priority queue or priority structure, right? And we check the best one first. Again, what's best, that depends on the problem, right? In a map situation, could be a distance, could be a cost, actual cost of going, right? Ticket cost and so on, right? So now, right? So again, we talk about lots of Dijkstra here. So I'm not going to talk about this more, but I will lead to the other approach, which is, of course, depth first, right? Which is, in this case, where is it here? All right. We could do depth first, which means start, we keep going until we cannot go anymore, right? In fact, in many problems, this might be if if you are fine with a solution, right? And this might be a valid might be a better approach to depth first. You just go as deep as possible, and if you suspect that this kind of problem leads to many solutions, right? And you just need any solution, then depth first, right? Might be the preferred one over the breadth first, right? You just keep trying, right? And maybe you'll get a solution, right? You make these moves, you make, and maybe you reach the goal, right? So, again, doesn't mean, again, both of them can be viable approaches, right? It just depends how much time you want to spend. Okay, yeah, all right, yeah, I think we're a little bit over time, so let's take a break till around 4:50, right? So we can finish a little bit early.